All right, so welcome to Math 344, the mathematics of sports. And so what I want to do today is, start talking about some of the mathematics, behind a lot of the stuff we're going to do. As this is, of course, the first class after the Super Bowl, it is mandatory in a math of sports class to talk about the Super Bowl. Eagles and Chiefs fans are not allowed to answer the following question: pass interference, yes or no? I'm curious, who says there was pass interference? Who says other things of similar level of pass interference were not called in the game? And this is where it gets really interesting in something like this, in terms of what is called, what is not called. So in honor of the Super Bowl, I thought I would show the evolution of Madden football. So this was the very first Madden football. And then, I'll leave the link for you to watch, at home in terms of just how video games have improved. I taught a class on the math of Lego, and one of the products you can buy now is a Lego Atari. So I actually picked up an old Atari emulator to show my kids what games we played when I was a kid. And this is going, wait, how do you move? Oh, the piece doesn't move. Got it. And so you see what the game looks like, and then when you jump towards the end.
Get cable-free live TV and access to add-ons like Sports Plus to watch NFL Red Zone. That's every touchdown from every game.
This is the video game compared to what it was like when I was a kid.
I think it's fair to say
just completely, absolutely different in terms of what the game is.
Something special there, boy.
The related question is, what do you do in terms of the mathematics to do video games quickly, to be able to do the computations quickly? Going a little bit earlier than the Madden football, this is the first football game I played when I was a kid. This was the Atari 2600 football. Okay. How many people remember what an eigenvalue eigenvector is? All right, so not everybody remembers entirely. So a vector is a quantity that has both magnitude and direction. A matrix, there's a lot of ways of viewing what a matrix does. A matrix often takes a vector as input and gives you a new vector as output. And typically, the new vector will have a different length and it will have a different magnitude. When you are writing down what a matrix does, you have to choose a coordinate frame. You have to choose the basis in terms of what you write things down. Typically, you would like to use the nice Cartesian coordinates. Maybe X is the east-west direction, Y is the north-south, but it doesn't have to be like that. And the same physical transformation can be written in different ways in different bases. This is not a class on linear algebra, but as I know we have some math majors, I just want to say a couple things sometimes at different levels. If when you apply the matrix, the new vector is in the same direction as the original vector, we say it's an eigenvector, and the eigenvalue lambda is the number such that A times V is lambda times V. We do not consider 0 to be an eigenvector. Why? Well, any matrix acting on 0 would just give you back the 0 vector. So if we chose 0 to be an eigenvector, it would always be an eigenvector, and it would not have a unique eigenvalue. Any lambda would work because anything times 0 is 0. So eigenvectors are always non-zero vectors. It is possible that the eigenvector is 0. That's fine. It's just that the eigenvalue is 0. That's fine. But the vector itself is not allowed to be 0. So for example, if I give you the matrix 1, 2, 2, 1, and I take the vectors 1, 1, and 1, negative 1, I see that in the first case, I get back 3 times what I started with. And in the second case, I get back negative 1 time. The first one would be an eigenvector with eigenvalue 3. The second would be an eigenvalue with value negative 1. Why are eigenvectors and eigenvalues so useful? Well, a lot of times in mathematics, we want to apply a matrix multiple times. And by multiple, it could be thousands, it could be tens of thousands, it could be even millions of times. If you keep changing the direction of the vector, it means this becomes a very long, tedious calculation. There are some advanced ways you can arrange the calculations to minimize how many computations it costs to multiply matrices together, but it's still going to be expensive. If, however, when I have my matrix acting on a vector, if it just rescales the vector, well, if I multiply it by the matrix again, instead of having 3 times, I'd have 9. If I did it again, I would have 3 cubed or 27. And then it makes it extremely easy. And then the hope is that we can write a typical vector. So we'll call this, say, 3v1. We'll call this -1v2. We can write a general v as, say, c1v1 plus c2v2. So if I took a to the nth power on v, after you do a little bit of algebra, it would just be c1 3 to the n v1 plus c2 -1 to the n v2. And so if I can write any vector as a combination of v1 and v2, well, a matrix applied to a sum of vectors is the sum of the matrix applied to the vectors. And then I can just pull out the c1 and c2, they just rescale. And this allows me to really easily compute high powers of a matrix A if I can write any vector. Well, if you think about what 1, 1, and 1, -1 are, if you look at the standard coordinate system, 1, 1 is a vector in this direction. 1, -1 would be a vector in this direction. And we see that, oh yeah, that's going to be a great coordinate system to use. They're perpendicular, which is really nice. And what's really looking in the background here is that for different matrices, there are different bases that are more natural than others to use. And depending on the transformation I give you, one basis is going to be better than another, and it might just make easier calculations. So I can calculate really high powers. At this point, we don't necessarily know why we might want to calculate high powers, but that's something we can do. Not surprisingly, by the end of today, we'll see an application of this to sports. Okay, so let's solve the Fibonacci problem. So this is one of the most important equations of all time. The sequence is typically given as 0, 1, 1, 2, 3, 5, 8, 13, ... where each term is the sum of the previous after I give you the initial conditions. And so if I let Vn be Fn -1, then Vn plus 1 would be Fn plus 1. Fn plus 1 is just Fn plus Fn -1 Fn. And so if I take the vector Fn -1, it would be 1, 1, 1, 0. And then that would just be 1, 1, 1, 0 times the vector Vn. So we get Vn plus 1 is just, let's call it AVn, which would be a squared Vn -1, equals equals. So how many powers of 8 do I have when I'm hitting V1? N. And the way I can always figure this out is 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. I've got a 1 here. So this tells me that Fn plus 1 Fn is equal to 1, 1, 1, 0, acting on the vector V1, 1, 0. And that's just the nth power. So if I can compute a high power of this matrix, or if not a high power of this matrix, if I can compute what this does to the vector 1, 0, I can actually write down the Fibonacci numbers. So I need to find what are the eigenvalues and what are the eigenvectors of this matrix. So I want to solve AV equals lambda V. So I'll leave this as an exercise for you to try to finish this if you want. So, again, if you've done linear algebra, this is a nice way to review what you're doing, find the eigenvalues, find the eigenvectors. This is a small matrix. If it's a small calculation, you can just roll up your hands and just do it. You could, of course, also go to some online programs like Mathematica and say, here's my matrix, what are the eigenvalues, what are the eigenvectors? and it will find them for you. The method people typically use is they solve the determinant of a minus lambda I equals 0. That gives you the eigenvalues, and then once you have the eigenvalues, you solve. You would never do this for a 10,000 by 10,000 matrix. You would not want to solve a polynomial equation. But this is going to be a quadratic. This is solving 1 minus lambda, 1, 1, negative lambda, determinant equals 0, or 1 minus lambda times negative lambda minus 1 equals 0. Okay, I can solve that quadratic without too much trouble. Once I have those lambdas, I then find what v solves AV equals lambda v. Once I have those, I then write 1, 0 as a linear combination, and I can do this. And when the dust settles, you get one of my favorite results in all of mathematics, Benet's formula. You'll get Fn is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. What I love about this is, what can you tell me about the Fibonacci numbers when you see that sequence? What word would you use to describe those numbers? So when you see numbers 0, 1, 1, 2, 3, 5, 8, 13, what's true about all these numbers? What property do they all have? They're all positive. What else? What kind of positive numbers are they? Integers. When you see things like 1 over root 5, 1 plus root 5 over 2 to the n, you've got square roots, you've got divisions, yet somehow everything cancels and you're left with an integer. This also allows you to immediately jump to an answer. You want the billionth Fibonacci number? I just plug it in equals a billion. And I don't have to add all the stuff between. When we do some simulations, can we just jump to the end of the game, or do we have to simulate and go through? The more things we have to simulate, the longer it takes. And so again, what I like about this problem is the idea that you might not have to go through all of the steps. There may be a faster way. Now, can somebody tell me roughly what's true about this number 1 minus root 5 over 2? It's negative. Can somebody give me any information about this negative number? Is it around -8, for example? So it's a negative number, and it's greater than -1. Do we all agree that the square root of 5 is a little bit more than 2? So this is going to be, the numerator here is going to be less than 2 in absolute value. Divided by 2, it's going to be less than 1. So you have something less than 1 and you raise it to a huge power, that's going to 0. So we know that this second term is going to be going to 0 as n goes to infinity. So the nth Fibonacci number is actually just whichever integer is closest to this part over here. It gives us a really good, fast formula for computing stuff like this. All right, cultural extra credit. I am not expecting anyone to get this. What movie has the countries Fredonia and Sylvania? You have to really know old movies for this one. So what I want to do is I want to describe a Markov process. So at every moment in time, I have a transition between various states. So my two states is I have Fredonia, and I have the evil Sylvania. Okay. And each person at every moment in time has a choice. They can stay where they are, or they can move to the other country. All right. So let's say if you're in Fredonia, some percent of the time you stay, and some percent of the time you go down to Sylvania. Let's say maybe 80% of the time you stay in Fredonia, and 20% of the time you go down to Sylvania. And similarly, if you're in Sylvania, maybe we have its transition probabilities. Maybe 70% of the time you stay in Sylvania, it's not quite as good as Fredonia, and 30% of the time you flee. And then I can give you some initial population. So we start with maybe A in Fredonia and B in Sylvania. Maybe I guess Sylvania only has one N. And I want to figure out what happens in the limit. And again, of course, in this model, you might get to a point where you're 3/5 of a person or 2/9 of a person has to move from one place to another. Let's just assume we can have fractional people moving, or that the numbers are just so large that that's not going to really matter. What do you think is going to happen in the limit? Do you think it's going to converge? Do you think it's going to have wild population fluctuations? What do you think is going to happen? And if you don't know, try to look at some extreme cases, build some intuition. What are your thoughts? What might be a nice, easy condition to start with for the populations? Yes?
Everyone is in one.
Good. Let's say everyone is in Fredonia. So if everyone's in Fredonia, then initially there's nobody in Sylvania, and as time passes, people start moving into Sylvania. And then people start leaving Sylvania for Fredonia. But what happens to the people when they go to Fredonia? They're more likely to stay in Fredonia than to leave. So the population of Sylvania is going to start to go down. But if there's a lot more people in Fredonia, you're going to have more people going from Fredonia to Sylvania in the beginning than Sylvania to Fredonia. But as time passes, what do you think will happen? So the population of Fredonia is going to be going down. Even though people are more likely to stay in Fredonia, there's so many people in Fredonia initially that the population of Fredonia is going to be plummeting because only a small number of people are coming up from Sylvania. But then what happens as the population of Sylvania gets larger? So initially we had so many more people in Fredonia that it didn't matter that people were more likely to stay in Fredonia than Sylvania. You're going to have a lot more people leaving Fredonia for Sylvania. But what's going to happen as the population of Sylvania gets larger? So eventually the population of Sylvania will start to decrease, which means the population of Fredonia. And so as the population of Fredonia increases, what's going to happen? And then, so is it going to oscillate between various extremes, or do you think it's going to converge to some steady state where there's going to be a fixed population of Fredonia and a fixed population of Sylvania? That maybe we're going to come to some very natural point where the number of people leaving Sylvania for Fredonia is equal to the number of people leaving Fredonia for Sylvania. Because if that happens, we then end up in an equilibrium. So it makes sense that we could be maybe fluctuating. It also makes sense that we could end up in some kind of limit. So this is our goal here, is to come up with a very simple model. Eventually we want to apply this to sports because this is the math and sports class. But let's start off with a very simple problem of just two countries and two choices. Whenever you're trying to do something, I can't emphasize enough how important it is to start with something simple. Anybody know roughly how many countries in the world? Yes.
210.
Is that high?
Yes, I think it's around there.
Okay, I thought it was a little lower. I think you're definitely within 50. So somebody will probably Google this very quickly. Are you going to Google this? Okay. I thought it was like somewhere between 167 and 187, and maybe 195. A lot of it's a question of, what do you call a country? And that can become, 195. What did I say for my upper bound? I said 197. Okay, so I just made it in my window, but not by much. Okay, we don't want to analyze a very complicated system with 197 countries looking at all the different possibilities. let's do 2 first and see if we can figure this out. So what we have to do is we have to figure out how do we want to model this. So let's call maybe, Fn Sn is the population in each at time n. And I want to model this. I want to know how much do I have in each at time n plus 1 as a function of how much I have at time n. So how many people will I have in Fredonia at time n plus 1? So can somebody give me a formula? Yes.
0.8 Fn plus 0.3 Sn.
Good. And then similarly, Sylvania would be 0.2 Fn plus 0.7 Sn. Yes. And so that would be 0.8, 0.3, 0.2, 0.7 Fn Sn. So what can you tell when you look at this matrix? What do you notice? So there's a couple of things that you can notice about this matrix. What do you notice about the entries? Excellent. So columns add to 1. It's actually called a doubly stochastic matrix if the columns add to 1 and the rows add to 1. The columns always have to add to 1. This is a transition matrix. It's basically saying, what are my probabilities of going somewhere? Well, it's got to add up to 100%. Also, entries non-negative. And they're between 0 and 1. Can anybody look at this matrix and easily see an eigenvalue, eigenvector? Or at least, if not an eigenvalue, eigenvector, at least an eigenvalue? Ah. Does somebody have access to Mathematica to quickly punch this in and see the eigenvalues? I can look at this and I can see an eigenvalue very easily. So the matrix A is, was it 0.8, 0.2? Yes. So 0.8, 0.2, 0.3. A transpose is 0.8, 0.3, 0.2, 0.7. What do you know about the matrix A and A transpose? What relation do they have with their eigenvalues? The same. So we're solving, we want determinant of A minus lambda I equals 0. That's the same as the determinant of A transpose minus lambda I equals 0. A and A transpose have the same eigenvalues. They may not have the same eigenvectors, but they have the same eigenvalues. When I look at this matrix, 0.8, 0.2, 0.3, 0.7, can you see one of the eigenvalues?
One in the eigenvector.
Yes. So I call this the Bula-Bula theorem. And the reason is I went to Yale as an undergraduate. Bula Bula was one of our chants, and I was a graduate student at Princeton. So to piss off the Princeton students, when I was teaching linear algebra, I named it after Yale. And so there's two parts to the Bula Bula theorem. One Bula is that because the rows sum to one is an eigenvalue, and the other Bula is one is an eigenvector. So you get one is an eigenvector with eigenvalue 1. So if you've done linear algebra, you should know that the sum of the eigenvalues is the trace of the matrix. So lambda 1 of A plus lambda 2 of A is the trace of A, which is 0.8 plus 0.7 is 1.5. Since lambda 1 of A equals 1, must have lambda 2 of A equals 0.5. So I can actually find the eigenvalues without any trouble. And then what you want to do is you want to find the eigenvectors. And so I'll leave this as an exercise for you to figure out. And again, I strongly encourage you, if you haven't done linear algebra in a while, to try to do this calculation. And now try to find, find V1, V2, write F0, S0 as, C1, V1 plus C2, V2. What is the limit as n goes to infinity of Fn Sn? Does this converge or does it oscillate? Okay. The problem is at least well defined. The question is just, what is the math going to say? And so if you think about what the eigenvalues are, it should actually tell you what's going to happen. Okay. Everybody clear on this? So again, strongly urge you to go through and try to solve this problem. This is a very simple example of you're trying to model what happens over time. I have these transition probabilities. How many of you have done orbital bonding theory in, say, chemistry or physics? All right, so I will look at you. So you can talk about the different possible transitions. When I put in some energy, I can excite the electron to different states, and different amounts of energy will be maybe radiated outward, or it can fall down to different states and emit. And I can talk about what is the probability I transition from one state to the other, and what are the consequences. I maybe fall from this one down to this one, and I release this much energy. This is going to be very similar to what we will do in baseball. Okay, we have a couple of events, and we want to know what are the probabilities of transitioning from one to the other, and as you transition, what happens? The difficulty is, of course, finding these probabilities. Then you can ask, how much do things change if I adjust the coefficients just a little bit? One of my favorite homework problems I had when I was an undergraduate was in a differential equations class, where unfortunately humanity overproduces and we die of starvation by too many people going for too few resources. So a fleet of benevolent aliens comes to Earth and starts harvesting us. At what rate must they kill us to push us to a different part of the population spiral so that we will not overconsume the resources? And can you push yourself into a different equilibrium? How stable are answers? If I have a limiting behavior, if I change the 0.8 to 0.7993, it's not much of a change. How much is that going to change where we end up? If I have a pendulum, this is my cheap pendulum, right? How many equilibrium points does a pendulum have?
Is it flexible or is it?
This is going to say, let's say this is a perfectly rigid pendulum, not this cheap mouse. 2, hanging directly down or hanging vertically upward. Vertically upward is unstable. A small push leads to wild motions. If it's straight down, a small push gives very small changes. So you always want to see not just what kind of solution do I get, but how stable is the solution. If I change my initial conditions slightly, if I change the transition probability slightly, what's going to happen? And the reason this is so important is you need to know, how well do I need to understand One of my former students has done a lot of work with climate models and global warming. I am not going to say in this class whether or not global warming is happening or not, whether it's man-made or not. What I will say is he has found that if you change some of the parameters in the models that are being used by very small amounts, you get wildly different predictions, which is very concerning as to how confident are we about these values that we're putting into the models. For a more applicable short-term thing, think about the Ferguson model from Imperial College, which was used to justify COVID lockdowns. If this model is correct, millions of people will die if we don't do the lockdowns. But do we trust the model? Do we trust the parameters that are being inputted? And these are things you really need to think about as you are coming up with ways to attack problems. Right. So what we're really doing is we're talking about transition matrices. So we're trying to talk about the probabilities from going from one state to another. So if I give you a bunch of states, so if there are n states, how many transitions? How many ways can we transition? What do you think? Yes. Good. So each state has n possibilities. There are n possibilities for each. Right? Yes.
Would it not be n minus 1? You're in a state.
But you could stay at that state.
Okay.
So for some things, you cannot stay in your state. So in baseball, if we're looking at the configurations, can you end the at-bat in the same state as before? So look at the base configuration. Okay. So first, second, third, 0, 1, 2 outs. Can you end at the same state as when you started? Yes.
If there's like a ball, like, do you mean like after hitting the ball?
After hitting the ball, can you be in the same state as when you started? Yes.
The score change.
Yes, the score can change. Then you can be in the same state. You could have bases empty and hit a home run. You could have a runner on second and hit a double. So you could end up in the same state with a difference in score, but you could end up in the same state. And so we do want to allow the possibility that you could end up where you started. So in general, we will have a bunch of possibilities. And so your one possibility is just looking at all the different paths I could take. And then, so does anybody recognize what I'm drawing? I'm drawing a complete graph, but I will also draw the ability to go back to where you started. Right? So how many probabilities do I need to give you? Oops, I missed one. Sorry. And I've got to be careful because for each one of these, I actually have to give it to you in both directions. Because going from one state, from state 3 to state 5 might be a different probability than going from state 5 to state 3. So how many different transition probabilities are there? Is what? So how many transition probabilities do we have? Yes.
For this one specifically?
Yes, we're with this n states.
Where there's n states,
It's just n squared. You could also write that as there's n choose 2 ways of choosing another state from the state you start with, right? That's the number of ways to pair 2 things. Each one has to be done twice. And then I have to add in n because I can go back for myself. Well, if I do the algebra here, that's going to be 2 n minus 1 over 2 plus n. That's n squared minus n plus n is n squared. So that's a way to just check and confirm that it really is n squared states. I have n states. Each state has n possibilities of going to, so I have to give you n squared numbers. Once I give you those n squared numbers, I can now have time evolve. And I can talk about the probabilities I go from one state to another. So if I wanted to model a baseball game, all I need to know is what is the probability of transitioning from one state to another? What's going to affect those probabilities?
Previous states, like the odds of going, the odds of getting a triple are better if you already have the guy who's on second than the first.
So do you think you have a better chance of getting a triple if there's a runner on first or third, second?
Oh, my bad, bad terminology. I meant getting a guy to third base.
Right. So depending on which state you're in, there's going to be differences in terms of the probabilities of getting to the next state. Yes.
Each of those probabilities is different for every different battery.
Right. So different batters are going to have different transition matrices. And then your transition matrix might depend on who is pitching. It might also depend on what else. So what else might be important in terms of trying to figure out what's going to happen on a play? Okay, why the weather?
Well, I know they wouldn't play if it was in the rain, but if there's heavy wind or something.
So you could have some dependencies based on the ballpark, based on the weather. Absolutely.
Maybe the score.
The score, right? For instance, let's say it's a tie game, bottom of the ninth. As soon as a run crosses the plate, the game is over. And so certain states will no longer be actually accessible. Or you might have a different strategy. You know, if it's a tie game and you have a runner on third, no outs, what are you trying to do as the batter? I'm sorry?
Maybe fun.
I wouldn't say bunt. What kind of contact? Yeah, so it's tie game, no outs, runner on third, bottom of the ninth. You just need to score a run to win. Sack fly. Just hit the ball deep enough so that the runner can go. So that would mean that the defense now changes. The defense plays as far inward as possible. I'm sorry, as far back as possible so that if they catch the ball, they can still throw the runner out at home. They're happy to concede to you a hit if they are giving up the possibility of, well, I could have caught it if I played a little bit deeper, but if I catch the ball here, the runner is going to score. And so it doesn't matter if I get the batter out if the runner scores. So I'm going to concede a ball going over my head and giving you a single or a double, which would have been, an out, because I can't let that run score. The hope is when we're trying to calculate things, for a lot of situations, we can just say, we don't have to worry about this. To first order, most of the time, at least early in the game, we're in configurations like this. But when you're trying to model a game, especially late innings, and trying to figure out what strategy to use, these transition matrices are going to be very different. When you're looking at the probability of a batter doing certain things, it could also depend on who's batting after them. If you have somebody who's a really, really bad hitter after you, the other team might be more willing to walk you or give you certain types of pitches that are not easy to hit well, and change what your transition matrix probabilities are. So has anybody ever heard the phrase, keep it simple, stupid? This is the first principle of modeling. Don't try to incorporate everything. Very simple model, try to understand that. If you can't even do the simple model, there's no point in trying to do the more complicated one. This is why step one was Fredonia and Sylvania. We just have two countries and people transitioning between the two of them. Okay, how many of you have ever seen the run expectancy matrix? Great matrix in baseball. It tells you what the probability is what's the expected number of runs scored from each configuration? So this is what I found was the table for the 2019 season, and I know it's correct because I found it online. There's a store in South County that has a beautiful picture of Abraham Lincoln with the following quote, the problem with the internet is you can't believe everything you read on it. And so I keep debating, should I buy that sign and just put that outside my office? Are we confident that these numbers are correct? I found them, I spent like 10 seconds Googling. This is at least something that's pretty easy to count if you can write script and go through all the Major League Baseball games and look at all the different configurations and whatnot. So can anybody tell me what these stand for, the numbers up top? Yes.
Where the runners are.
Where the runners are. This is nobody on any base, runner on first, runner on second, runner on third, bases loaded first, second, and third. The columns are a little bit easier, 0 out, 1 out, 2 out. And so this is telling you that if there's 1 out and a runner on third, on average, teams score 1 run from that point onward in the inning. If there are bases loaded and 2 outs, you score 0.77 runs. So when you look, what would you expect to happen as you move towards the right? Would you expect the number of runs scored to be increasing as you have either more people on base or people in better positions? Seems reasonable. I'm not seeing any of these numbers go down, so that's at least a very logical. And as you increase the number of outs, it's really clear that you should have a lower chance of scoring. It can't help you to have more outs. So these numbers at least pass the first smell test. And so a lot of times when you try to figure out what is the value of an at-bat, or what is a pitcher's performance on the mound, you can look at what is the game state when you start, what is the game state when you end, and of course you have to include if there were runs scored, and then try to figure out, well, what was the contribution? Well, this bat, we had bases empty, 1 out. I expect to score 0.29 runs. I got a double. I now expect to score 0.72 runs from this point onward. Okay, that difference is going to be my credit. Whereas the pitcher, if there was 1 out and I get the batter out, I was expecting the team to get 0.29 runs. Now the expected value is 0.11. So I can now give myself the credit for the pitcher for that. So this is a really quick and easy way to get a sense of the value of someone. There's a lot of things can happen in an at-bat. What are all the different things that can happen in an at-bat? You can strike out. You can walk, you can get a single, a double, a triple, a home run. You can be hit by the pitch. There can be a drop third strike, which counts as an at-bat for your batting average, but you could actually successfully run to first base. And then, of course, when you have base runners, there's all these different things that could happen. You could have a runner on first, and you could walk, so now it's runners on first and second. But maybe the defense is asleep. Maybe there's a huge shift going on, which will be illegal next year. And I've seen this happen in the playoffs, where they've shifted so nobody's covering third. So the batter walks and the runner goes from first to second. And then because no one is covering third, as soon as the runner from first hits second, they start sprinting to third. And because no one's there, they actually go from first to third on a walk. These are very rare plays. And so what you might just say, look, to first order, let's ignore stuff like that that's going on. When you try to calculate, what's the run expectancy for different configurations? Well, it depends who you have on base. If it's the bottom of the 9th and it's a tied game and somebody walks, what do you typically do after the batter walks? Well, let's say they get a double. What would you do after they get a double? So who knows baseball? Yes, you put in a pinch runner, because all you have to do is score 1 run. So you might say, well, I'm going to risk it now. I'm going to put in a pinch runner, because if I can get them across the plate, we win the game. So when you're trying to calculate these run expectancies, a lot of it is going to depend on who happens to be on the bases. If you have speedy people, you'll be more likely to score. All right, so here is, I went online and found they were averaging over several years what the run expectancy was in different configurations. And then they also looked at what is the chance that a run will score at some point in the inning. So you just want to know what's the chance that at least one run is scored. And then the last one was, how often each configuration happens. How many times are you in each state? Well, what I want to do is I want to figure out my transition matrix. For simplicity, what should we assume about all batters and all pitchers? Equal skill, they're all spheres, right? Everybody is equally skilled as a batter, everybody's equally skilled as a pitcher, every runner has the same speed. So the simplest model is everything is the same. Is this enough information to calculate the transition probabilities? So how many states do I have? Yes.
Is the difference between this, like you can't get from certain possibilities to other possibilities?
So some of the probabilities will be zero. You can't go from bases empty to runners on second and third. That probability will be zero. Do we know what the average number of runs scored in an inning is by looking at this? So can you look at the, yes?
It will just be 0 outs, no.
Yeah. Right. Shouldn't this be the average number of runs scored? Because each inning starts off with bases empty, no outs. That can happen multiple times. But if I want to figure out, at the end of the day, every inning starts off like that. So I claim that this should actually be the expected number of runs scored, in an inning. I want to calculate all the transition probabilities. Is there enough information here to calculate this, or do I need more information? And if I need more information, what is that information? So your homework is to think about whether or not this is enough information. And if it's not enough information, what do you need? Rather than analyzing this, can somebody give me a simpler game of baseball? And if we can't answer the question in that case, we probably can't answer it in this case. What would be the simpler version of baseball? One base. So we have home plate and we have the base. And how about outs? 0 or 0 outs, and then 1 out in the inning. 0 outs, 1 out ends the inning. Or maybe 2 outs ends the inning. Maybe it's too simple if we only say that there's 0 outs. Try to do it in a very simple case like this. See if you can analyze in the simple case when there's just home plate. And of course, you have to keep track of whether or not a run scores. If you can't figure out that this is enough to uniquely determine the probabilities, do you think that the original problem is going to be doable? So again, general principle, solve something simple first, build from that. All right, so this is a good place to stop. We will continue with stuff like this on Wednesday.